huge round of applause to GitHub, Kelsey and Drew for hosting. Yes. Louder, louder. We are continuing to do mini talks this year, so if you want to dip your foot in the pool of public speaking about academic papers, we'd love to have you. And don't be scared, because we can help. We are free to review your talk, help you out with topics, and to help practice and things like that. So, yeah.
Sign up. Yeah.
Sign up.
All right, we're gonna get started, and then our first speaker is Clark Breyman. I'm going to, ever since the last meetup, I started actually reading aloud the bioses, like the bios. It's like how you, no, it's bios. The bio. Okay, so the bios of the speakers, which are actually kind of nice, and then I tend to put some things that either may be true or not true. So let's see about Clark. So Clark is a principal engineer with Yammer's infrastructure team, where he applies a combination of code, OCD, and war stories to make life easier for our product engineers. He also holds a world championship on jitterbug swing, and when he's not fighting entropy, he enjoys San Francisco, Lindy Hop, yoga, and natural language processing. His mini today is going to be on the magical number 7 plus or minus 2. And let's give it a round of applause for Clark.
Howdy, all. Thanks again to GitHub for hosting. Thanks, Inez, for the opportunity. Papers we love. I love this paper, the magical number 7 plus or minus 2. A little bit about me, engineer at Yammer. I'm not a psychologist, nor am I particularly well versed in psychology. I just love this paper. This paper was introduced to me when I was an undergraduate in 1988 at UCSD in a music class, a psychoacoustics class. And I saw amazing parallels between what this paper was talking about, a paper written in 1956, and what I was studying in computer science in the late 80s. Things like subroutines and structured programming and object-oriented design and things like that. And it was just eye-opening. And it was also a valuable template for modular discovery, in that he found something that was a curious, seemingly universal phenomenon. He created a structure for interpreting it, applied it to a couple different examples, formulated a hypothesis, and then tested it. And regardless of whether the test comes out true or not, it was a basic building block of discovery, which I found really nice to see. Starts off with a great line. I have been persecuted by an integer. The persistence with which this number plagues me is far more than a random accident. Either there is really something unusual about the number, or I'm suffering from delusions of persecution. Not your typical academic paper. I love the tone of this paper. It brings up notions that magic numbers exist in nature. We see them in physics, we also see them in psychology, and they can be discovered experimentally. The same approximate number shows up in multiple experiments of what is called absolute judgment, or being able to identify points in a continuum. And the same magic number reappears. Because the same magic number reappears, we must ask ourselves, is there a connection, or is this really just separate random occurrences of the same number? And in 1956, we had a new tool for this, which was information theory. People being able to come up in psychology and say, hey, what are the new tools coming into my toolbox that I can use? To draw that out a little bit, he says the observer is considered a communication channel. He actually makes use of analogies to a telegraph at some points and radio waves in other points, in that if you take a value and that value doesn't vary at all, it can't give you any information. If that value varies all over the place, it might be able to give you information. And if you actually have two values, an input and an output, and they're highly correlated, then that is a communication channel that can transmit information. So a human being is considered like this radio receiver that if I can send something into his or her eyes, their ears, the taste buds, and they can recall and transmit what they've experienced, that's a communication mechanism. And the fidelity with which they do that is the channel capacity, the upper bound on the information that they can transmit. So working with that, he also even goes in to elaborate in 1956 for the psychology audience the concept of a bit, a single yes or no judgment, as the fundamental unit of information, also highlighting that information as variance is without units. It can be used to characterize and look at things from experiments regarding sound perception, taste perception, visual perception, and because it has no units, you can actually look at and compare values that you get from different experiments in different senses to make judgments. Now, the first judgment he looks at is absolute judgment, unidimensional judgment. In a single dimension, something like pitch, loudness, salinity, visual interpolation, those sorts of things, he sees that people find 6 values plus or minus 3, or turned into a bit equation, 2.6 bits with a standard deviation of 0.6 bits. When he looks across a variety of experiments. And that's really, really low value given how much information we capture every day. We can discriminate between people's faces. We can discriminate between people's voices. Why is this so small? We know that we can add dimensionality. We can say, okay, let's look at 2 dimensions in visual interpolation, or let's look at salinity and glucose in taste at the same time. Can we improve the information density or the transmission of information that way? And the answer is yes, but not linearly. We see maybe 1.5 times the amount of information when we have 2 dimensions. And he makes a hypothesis here that evolutionarily, in order to survive a constantly fluctuating world, it was better to have a little information about a lot of things than to have information about a small segment of the environment as a survival tactic. Now, he builds on this with the notion of subitization, introducing that as basically the threshold between when you start estimating based on an input signal and when you simply enumerate. If you can enumerate values, and typical experiments regarding subitization max out at basically saying, once you hit 6 or 7 values, people start estimating. So he has this question, I see 7 everywhere. What am I going to do about it? How am I going to be able to think about that value of 7? And so I go into immediate memory. Is memory a mediator of this, or is it a tool for expanding my ability to transmit information? Is it a tool for exceeding this bottleneck of absolute judgment, or is it also intertwined with that mechanism? And so he goes on to note that immediate memory is experimentally determined to be, surprise, 7 items in a sequence for most things. And so going on from that, he has this hypothesis that these are the same process. I've just shown you that the span of absolute judgment can distinguish between about 7 categories, and the span of attention will encompass 6 to 7 objects at a glance. What is more natural to think of that all these aspects are a single underlying process? So here's this unification hypothesis. We have this single tool, information theory. We apply it to several different occurrences. They give us a similar result. Let's try to unify it and test it. So we have a test for the hypothesis. We have immediate memory holds a fixed amount of information. We have these 7 things in immediate memory, and we have absolute judgment being roughly 6 plus or minus 3 or 7 plus or minus 2 things. Is this mean that if the information density of the items is small, we can remember more things, and if the information density is high, we can remember fewer? And he goes on to summarize 2 separate experiments by Hayes and Pollock that actually disprove his hypothesis. Repeating sequences of items of different information densities, either number sequences, phoneme sequences, word sequences, and they find, specifically Pollock finds, that information transmitted increases nearly linearly with the information density of the items. So he draws this out and saying in information theory, this means that bits of information in an individual value or an individual item are different from the chunks of information in a sequence that we work with, or the members of a set. So you can have very, very high density information or very, very low density information, and it is an independent parameter from the number of items in a set that you can remember. That's really, really valuable because when you take into account human behavior regarding recoding, which we do in computer science and compression, basically saying that if the incoming data stream has pauses between chunks and the incoming data stream is low density information, our brains can recode this to higher density information so that we can perceive that we actually remember lots and lots and lots of binary digits. And he goes on to describe an experiment where somebody trained himself to remember long sequences of binary digits because he trained himself to be able to recode those binaries as octal in a much, much faster manner so that as the bits came in, he could recode them as octal and his short-term memory wasn't as taxed. So this is all cool stuff. I've disproven my hypothesis, but I've gotten some basic principles to work with. So what this all means is that absolute judgment and immediate memory are limited. Increasing dimensionality and chunking transmission are tools for breaking this bottleneck. Furthermore, recoding is important. When there is a story or argument or an idea that we want to remember, we rephrase it in our own words. We recode that in a manner that is optimal for us. And lastly, information theory provides a quantitative framework for getting answers and comparing experiments, especially comparing experiments across domain. Now, what this means about the magical number 7, he punts. He says, I suspect that it is only a pernicious Pythagorean coincidence, and just stops right there. He doesn't tell us what's magical about it. He says, I looked for magic, I couldn't find it, I don't know if it's there, but it might be just coincidence. Now, for me, why do I love this paper? I think we're all limited creatures, and I want to create things as an engineer that can be understood, used, and maintained in spite of our limitations. I want to build human things. Papers like this give us the knowledge and power to avoid building things that exceed our cognitive limits. But they also pose questions to us as designers. How do we ensure our system's design does not challenge cognitive capacity? How do you structure naturally flat domains to improve comprehension? I think of SOA designs, microservices designs, function libraries, all of those flat structures. We need to impose our own structures on in order to make them work within cognitive capacity. And that's my talk. Thanks.
Do you want to take questions? Questions?
So I agree the tone is great in the paper. What I thought was the most surprising result was the multidimensional analysis, which he sort of passed over and you mentioned, but what weren't in your conclusions either, that when you have this way and that way and that way, you can transmit more information, but it's fuzzier. And I don't feel like anybody has tried to leverage that in UI design and systems, et cetera.
Yeah, he does actually make a cool point buried, but he sort of like throws it out there without any elaboration or any backup or anything like that, saying that the perceptual dimensionality he suspects is asymptotic to 10, so that you can't actually get more than 10. But he actually also goes into a Pollock experiment where he was able to actually boost individual items to like 7.2 something based on sort of linguistic models and what you'd think of as sort of binary features from a machine learning training set these days, which is still, the fact that he was doing this in 56 is still mind-blowing.
Any more? Questions? No? All right. A round of applause for Clark. Thank you so much. I'm waiting for you. Yes. All right. So Devon today is going to talk about non-blocking algorithms and scalable multicore programming. And this is a little bit about Devon. Devon is a recovering competitive guitar hero and rock band addict. Today, he's a software engineer at Fastly, where he contributes primarily to the performance and debugging of low-level systems. In his former life, he used to be an antiques art collector, and he specializes in 16th century portraits of peacocks. His experience over the last 15 years ranges from web applications to embedded systems firmware and most areas in between. His primary technical interests are developing and debugging high-performance, concurrent network system software and related tools. So let's give it up for Devon.
That was a mouthful. And just to preface this, I wish I had seen that previous talk before making my slides, because I think I might have made them a little denser in terms of packing information closer together. So this is about a paper on non-blocking algorithms in scalable multicore programming, as you may have guessed, written by Sami Albarra, who's a friend of mine and a really awesome engineer So a little about me. I'm Devon Odell. I'm a huge Zappa fan. There's a picture of me and Dweezil Zappa where I have a little bit less hair and body mass. So I'm a software engineer at Fastly, as Inez said. And performance is something that I care passionately about. So it's one of the reasons that I really love the paper. So just to get into what we're going to be talking about a little bit, I'm going to go through sort of an introduction, which I guess I've already started. We're going to talk about environmental considerations in the design of software, and this is really more on the hardware side of things, but environment, when I say that, I'm going to cover it a little bit more, but I really do mean full environment, whether that's the hardware, runtime environment, libraries, building, whatever. We're going to use that information to explore non-blocking algorithms, the guarantees they make, how they function under contention, what linearization means, and a little bit about safe memory reclamation. And then we'll wrap up and cover all the topics. So this is a screenshot of the paper, which I hope at least some of you read so that you can give me a hard time after this when I'm wrong about everything. It's an industry paper. It's not an academic paper. So hopefully there will be at least some information in here that you can take back and use. So why do I love the paper? Apart from the points that I've listed on the slide here, it really helps us understand practical considerations for designing and using non-blocking algorithms and data structures. And it gives us a really good basis for understanding our environment in the context of parallel and concurrent software. And also, apart from the issues with composability of traditional lock-based parallel programs and lock-based synchronization in parallel software and concurrent software, people with experience in the field will also recognize sort of the performance issues that are inherent with developing lock-based software in fields of high contention. Thank you, Gordo. So this paper helps us recognize contention, understand what it is at a fundamental level, and what we can do about it. So to start off, let's sort of discuss our environment and what that means. So this is a deep topic, heavy paper, covers a lot of material, and it can be pretty hard to digest. It took me certainly several readings of it, and I actually looked over it a few times before it was submitted to the queue. You also need a little bit of experimentation on the material that's covered in to really get it correct, or at least I did. If you're not working on system software, so maybe you're working on web stack software, or maybe you do user interface stuff, I gather this is a relatively wide range of people in the audience. You might be asking, well, what am I going to get out of this paper? And the biggest takeaway that I think is generally applicable is that understanding your environment really, really matters when you're writing software of any kind, really. But in particular, if performance and scalability are goals of yours, you can't get anywhere without understanding your whole environment. And the bulk of the paper is really talking about the execution environment and environmental considerations. So what do I mean by environment? As I said, there's 50 things that you might think of: programming language, compiler, continuous integration suite, your build tools, processor, hardware. And I do literally mean all of these things. The paper consistently highlights environmental considerations to do with language choice, processor, compilers, and hardware. Furthermore, the further up the stack you are, the more environment you actually have. So just because you're at the UI level doesn't mean you get to ignore everything under you if you're concerned about these points. If you're writing web UIs or user interfaces of any kind, if you're writing web applications, there's actually more stuff running under you to provide your environment. And you need to understand that to actually make a true full stack claim. And if you treat everything below a certain level as a black box, you're eventually going to run into problems with everything at or below that level as soon as you try to deal with scalability and performance, especially, or debugging for that matter. So to ease into the topic, we'll talk about one of probably the harder bits of the paper to sort of understand, which is about processor caches and cache coherency. And the cache we're talking about here is literally a memory cache. Modern processors have multiple levels of caches. There's level 1, level 2, level 3 cache, also sometimes known as last level cache. You can think of registers on a processor as a kind of cache. And each level can cache more data. The caches are continuously growing, generally. But each cache is also farther away from the processor physically in terms of maybe on core, next to core, on maybe a system bus, and then finally you actually get out to memory. And the reason that the cache exists literally has to do with the propagation of speed of light through silicon, and this is why the distance to the processor matters. The closer the data is to the processor, the faster it is to access, right? And we are talking about something that's closer to light speed than I think any of us probably can reasonably understand in our heads. So from a physics perspective, it takes measurably more time to fetch data from memory, which is inches away from a processor, than it does to fetch data from a cache, which might be micrometers away or millimeters away. There are other reasons that accessing RAM can be slow. We'll get onto those. But first, to quote the paper on cache coherency, understanding the mechanisms that provide coherency guarantees on multiprocessors is a prerequisite to understanding contention on those systems. Oops. So what is contention? Why does it matter? Contention is when we have many processes involved in a system and these processes are attempting to share memory with each other at the same time, okay? And understanding contention matters because if we do a poor job at managing it, our software is actually going to suffer in terms of performance. So this is a diagram of the MESIF cache coherency protocol state machine. It's probably important to understand all of the states. The paper does actually talk about state transitions a little bit. I'm not going to get into that too much because to actually describe the protocol, I have to talk about write probes, bus reads, bus snooping, read for ownership, and these aren't really topics I want to get into because you could literally do an entire talk or in fact write an entire book on the topic. So I count 17 distinct state transitions between 5 different states. That's a lot. What are the states? Well, in terms of state space, right? That's actually pretty big. M stands for modified, which means that memory has been modified, it needs to be flushed. S stands for shared, which means that the memory is shared with another core. E stands for exclusive, memory is owned by the core. And I is for invalid, which is we know that our copy of this memory is invalid. So these are the names of the state of the cache line. That's already a lot to digest. The F is not for effing complicated, by the way. F stands for forward. It's an optimization state that basically all memory enters the cache in forward state. And it allows the processor to optimize requests for memory by having only one core respond to memory requests instead of having to broadcast responses from everybody who knows about the memory and choosing. So we have this reasonably complicated protocol for sharing memory, and it's implemented on our processor. And it's implemented so that we don't have to read from memory, which is where all of our data lives, where our software is executing, loaded into and executing from, right? So we're trying to actually not use the thing that's fundamental for all of our software to execute. So it exists to manage sharing of the data. What actually makes up the cache? So a cache consists of cache lines, and the cache line is the granularity at which coherency is maintained on a cache-coherent multiprocessor system. The cache line is also the unit of contention. So you can think of a cache line as a sort of hash table entry, and the cache is a hash table of sorts. Each entry associates a 64-bit address as a key with a 64-byte memory value. There's an index into the table. It also stores the state that the cache line is in. So there's a number of relevant points illustrated by this figure, which, by the way, comes from the paper. With each box representing a core, we notice that processors have a topology. Now, these may be individual sockets. They may be different cores on one socket, on one physical processor. But that doesn't really matter too much because different processors do different things, different architectures. So you can think of it either way, whatever is easiest or more comfortable for you. We see that each core in this example has its own level 2 cache. We notice that memory might be shared between the cores. So the third item, so the second index, or the index with value 2, is shared between both cores. We also notice that sometimes we might have to ask a remote processor to read memory that's not local to us. And we see this because there's a memory interconnect between the processors, or between the cores. And this is actually connected to different sets of physical memory. Back to caches and cache lines in particular. On modern Intel processors, cache lines are 64 bytes. I think power is 128 now. But this sort of is an architecture-dependent kind of thing. But what about this idea that cache lines are the unit of contention? If I write 8 bytes of memory to any particular address, eventually 64 bytes are going to get flushed back to memory. Similarly, if I want to read 8, 16, 1, 2, doesn't matter, any number below 64 bytes from memory, I have to read 64 bytes of memory into the cache. So this is why the cache line's the quantum of contention. Reads and writes of any size are always translated into the line size at an aligned address. So if we have many processes on many cores trying to read and write to the same memory, the same 64-byte space, we have contention, and we're said to be contending on a cache line. In this case, the line state's constantly changing when we're reading and writing from multiple processes. The state, the modified, shared, exclusive, invalid, it's constantly changing due to the writes happening from discrete cores. So how does this manifest in software? So I've basically taken a code snippet from the paper. I've translated it a bit to fit the slide format. But let's go over this and see what this actually says. There's a hint at the top that we have 8 threads. We then have an array that contains 64-bit values, so 8-byte values. And in C, this is an array. So the memory for those values will be contiguous. All of the values will be next to each other. And because we have 8 threads and 8-byte values, therefore, we have filled a cache line, right? We've got 64 bytes of contiguous data. Now, furthermore, if all of these threads are executing this thread function, which simply increments a value while the thread is running or is not being signaled to exit, there's going to be a ton of traffic on the cache coherency bus, on the bus that's sitting there to connect the processors together so that they can basically gossip about what they know about memory between each other. The cache lines are going to transition from invalid, shared, modified, owned, or forward states. And all of these transitions need to be broadcast. So this is a pathological worst case, but it's actually quite common to find in modern software. Effectively, every read has to come from RAM, because basically we can guarantee that our copy is probably invalid. We've got 8 threads trying to do something, so we've got a 1 in 8 chance that we actually own the cache line. Latency and bandwidth to memory are obviously more constrained from the CPU, because otherwise why would we spend all this time having all these different levels of caches? So forcing reads and writes to go to memory means that we increase latency physically farther, and we decrease throughput. And there's actually a correlation between the two that we'll get to a little bit later. But because we're tying up the cache coherency bus with state machine traffic, this is said to be called false sharing, is the term for this, because we have a cache line that's being used by multiple threads, but the data is not actually related. So we're sharing the memory, but we shouldn't be. So this is why it's called false sharing. And because of the traffic, this is going to impede the performance. So how do we solve this? So the first thing that we can do is we can pad the data structure. And so I've just added, 56 bytes of padding at the end, which means that I've got 8 bytes for my counter, 56 bytes of stuff that I'm never going to touch. And because this is contiguous memory, the next slot is 8 bytes. So everybody lives in a different cache line. And assuming that those cache lines hash to different slots, effectively, we don't have any false sharing going on. This can work sometimes. Other times, the increased memory footprint of the application can actually impact the performance of the system negatively, especially if you've got a large number of these objects, right? First you had 8 bytes, now you have 64. You have fewer of those that can fit in a page, so, well, maybe I shouldn't get into that. The paper, it references further reading on this topic, but a solution for this can often be to implement per-thread counters. So now that we've got this sort of basic understanding of how processors cache memory accesses, and that they actually do this in the first place, right? Let's talk a little bit about how processors access memory. So different architectures provide different guarantees, and by architectures I mean Intel, Spark, Power, ARM, commodity processors. They make different guarantees about when data is written to memory. They make different guarantees about when a request to read from memory actually is visible. So I'm sure that at least one of us, including me, has made jokes about guarantees of eventually consistent databases, right? Who hasn't joked at Mongo's expense? Yeah, no hands. Okay. So it's funny, but our processors are eventually consistent, right? The stuff that we're running on, we're depending on an eventually consistent protocol to define what memory looks like at any point in time. When we consider that caching of reads and writes, in particular, but also with potentially weak guarantees about when those reads and writes happen, I'm not going to enumerate all of the particulars of each memory ordering model. There's a lot to cover. The paper does. But we can sort of understand that they go from particularly strong at the top level with total store ordering, which is Intel processors and some Spark processors, to moderately strong partial store ordering, which is another subset of Spark processors, to relaxed memory ordering, which is particularly weak. And this is the memory model used on Power and ARM, and if you're a total geek, Alpha as well. So it's also worth noting that there are exceptions to total store ordering on Intel. There are cases where Intel will actually reorder memory access. I'm not going to get into that too much, but it does underscore the point that just because you're on a TSO architecture doesn't mean that you can just forget about this. And also, if you're trying to write portable software, you have to consider all the different environments that you're targeting anyway, right? And this gets us again back to the environment. So how do memory ordering problems manifest? So this code snippet arguably looks correct. Let's say that we've got a producer thread and a consumer thread, and these are running on distinct cores. Maybe they're affine somehow, or processors if you wish. The code looks correct. We've got something setting up a message, putting a value in it, enqueuing it, and then telling the consumer that it's ready. The consumer sits there spinning until it can read a value from the signal, and then it tries to read the value, and it does some operation on the value. However, due to potentially weak guarantees, especially in relaxed memory ordering systems, it's possible that the consumer thread will actually observe the ready signal as complete before it is able to observe the value that was stored in the message. So this is eventually consistent, and that's why. And there may not be implicit guarantees about when things are persisted to memory. So how would we ask for this? How do we say, well, I actually need a total order of operations to guarantee the correctness of my protocol? So we use memory barriers for this. They're also known as memory fences. And these are instructions that a processor provides to synchronize outstanding memory accesses. There are particularly strong memory barriers that wait for both stores to memory and loads from memory to complete. And then there are also partial memory barriers that will wait for only stores or wait for only loads to complete. So we need to be able to provide some guarantees on the ordering for correctness, as I mentioned. Where do we actually insert these barriers? So in the producer, we're going to insert a barrier after filling in the message structure. And what this barrier does is it ensures a consistent state of memory before the write to the ready variable occurs. And in the consumer, we also need a memory barrier. So this memory barrier ensures that the consumer is up to date with all of the memory operations that were done relative to the ready variable, which is shared. So this really shows why it's important to familiar. Well, actually, I'll talk a little bit. This is kind of like pseudocode, right? So what would a memory barrier actually look like? This would actually be sort of a macro or an inline function maybe that was some assembler that on Intel would be using the mfence, lfence, or sfence instructions, and also have something in there to prevent the compiler from reordering those instructions. So from a practical standpoint, that's what that would actually look like. But these points really go to show why we have to understand memory ordering and memory barriers in particular if we're going to be implementing algorithms that require total order of visibility to be correct, which many lock-free algorithms do, or all lock-free algorithms do. So I mentioned that some processors provide partial barriers, maybe all the commodity processors. I'm not familiar with every architecture. So if we wanted to use these to reduce the overhead, we'd put the store barrier on the producer side so that we would wait for all of the stores to memory to complete. We would put a load barrier on the consumer side because we're interested in guaranteeing the order on the loads there. So moving on. Let's get to atomic primitives, atomic instructions, primitives, better word. They're part of our environment because processors are part of our environment and the processor is providing us with these atomic primitives. And we need to use them in designing concurrent algorithms because we need some sort of atomicity, some indivisible set of operations to use to provide safety guarantees on shared data. So these instructions are not cheap, even without contention. Maybe this is even obvious, right? I'm talking about an atomic load or an atomic store. So I'm inserting an additional adjective to talk about how I'm accessing this data. So there's obviously something a little bit more complicated going on in that if I just do a load or a store, you might have some kind of racy behavior on this, right? And if you work on parallel systems and you've worked with lock-based synchronization before and you forget to put a lock around some shared data, for instance, you observe race conditions where people observe a value that's incorrect or potentially say you've got a lot of threads incrementing a counter. If multiple threads increment the counter at the same time without doing atomic operations, an increment is really a read, a modify, and a write. It breaks down to a read from memory, a modification, and a write back out to memory. So it's possible that two concurrent operations, two contending operations, would read the same value, increment the same value, and write the same value, and instead of having an increment of 2, you have an increment of 1, because the initial read was of the same value. So why are these instructions more expensive? Some of them imply a full memory barrier, or they imply full memory barrier semantics to guarantee the ordering, right? So that you don't have these races on data. And even on systems that may not need heavy barriers, so systems that already guarantee total order, a language or a library or compiler provided interfaces, like consider maybe sync.atomic in Go or GCC built-ins, atomic built-ins, they can increase the cost by adding potentially unnecessary memory barriers. So it might be true, for instance, on Intel that we don't necessarily need to put a memory barrier after a particular atomic operation, or maybe a partial barrier would have been sufficient. But the compiler and the library, the language, can't know how that access is going to happen, so it may put a more heavyweight barrier than would actually be necessary to implement a correct protocol. So what kind of primitives do we get? When we're talking about lock-free algorithms, well, processors provide a number of different atomic primitives, instructions, operations. So atomic reads and writes from memory, atomic fetch and add, increments, addition, subtraction, right? We also have more complex read, modify, write primitives. And some processors provide specific classes of these primitives, as I mentioned, addition, subtraction. One primitive found in many lock-free and wait-free algorithms is the compare and swap primitive. On Intel, this is given to us as an instruction, CMP-XCHG. Power and ARM give us a two-part interface called load link store conditional, which I'll refer to as LLSC, and I'll probably also say CAS instead of compare and swap moving forward. So how do these functions work? So atomically, we test a value against some other value. If they're equal, we swap in a new value and we say we succeeded. If they're not equal, we do nothing and we return false. Some implementations, Intel in particular, will actually return the value or can return the value that was read on a false result. And we can actually use that to our advantage. The paper goes into some ways that we can do that. With LLSC, we have a similar functionality, but the interface, as I said, works as a pair. Load link loads an address and sort of keeps track of accesses, whether those are reads or writes or whatever, to that address. Then we've got some set of instructions that run, and then we have our store conditional side. So load linked is sort of the read part of read, modify, write. When store conditional runs, we check that the original value hasn't changed, and this is sort of done magically by the processor. And the store conditional part performs the modify, write portion of read, modify, write. So there's a problem with this interface, and that's that instructions in between the LL and SC are sort of a critical region. They're a critical section. There's a finite amount of space that the processor has to keep a dependency chain of instructions and operations that have appeared to access the variable that we accessed in load linked. So we have some state that we have to keep track of in between the load linked and store conditional. And additionally, every time we call load linked, we have a finite amount of space that we can use to store addresses, right? Because we're also on the processor, so we're really small and we don't have a whole lot of space. So if you have contention when doing load linked store conditional, or even throw that out the window, even if there's no contention whatsoever. System-induced jitter can throw the primitive sort of way out of whack. So consider cases like preemption, or consider cases where the scheduler's running you and your scheduling time runs out, and it runs out in the middle of your LLSC. Or consider that you have a lot of threads running, and maybe they're not contending on addresses, per se, but you have lots of LLSC operations, and you run out of space, buffer space, for tracking memory that you've load linked. In this case, you run out, the store conditional fails, right? If the value was modified, if we lost track of the value either due to dependency chain explosion or number of values that we're tracking getting too high, it's possible to encounter cases where no threads make progress whatsoever. And furthermore, this is particularly difficult to debug because when you're looking at this in a debugger, all of the operations are completing successfully until the store conditional happens. And the failure actually happens in hardware. So this again gets back to understanding your environment and understanding the primitives that you're provided, because if you know, okay, I'm on an environment that uses LLSC, you might say, okay, well maybe there's something I can do about the contention, or maybe I can reduce the number of LLSC operations I'm using somehow. But it is particularly hard to debug. So let's move on to talk a little bit about Numa. We saw on our diagram that different cores have access to, potentially have access to different physical pieces of memory. This is called Numa, non-uniform memory access. Many modern architectures are Numa architectures. And this means that some processors have an increased cost for accessing some parts of memory, particularly parts of memory that are owned by a remote processor. So again, let's think about the earlier diagram. If core 0 wants memory that's attached physically to core 1, it has to send a request to core 1 to get it, and vice versa. So Linux and Solaris, possibly other operating systems, allocate memory in pages to you on a first touch basis, which means that the first time you access some memory, that memory is given to you on the processor that you touched it on, whether that touch was a read or write. The behavior is configurable, but that's the default behavior. So this means that if memory was allocated or accessed by processor 0 and all future use was by processor 1, there's no migration of this data unless you specifically request it. Therefore, the access cost is increased because every access has to send a request to the remote processor, which may then also have to go out to memory. So the worst case, and especially when you have contention, right? If you've got contention, you're sending a bunch of stuff to the processor saying, give me this memory, I'm reading it, I'm writing it, whatever. But you're always having to go to memory plus the additional hop. Furthermore, in other architectures, you don't necessarily have a one-to-one set of connections between processors. So it's not necessarily true that processor 0 and processor 4 can talk directly to each other. They might have to talk through processor 2 or processor 1. So you might have multi-hop systems. And we all know from networking, more hops, more latency, right? Generally. So unfortunately, tons of modern software is designed to work exactly like this, right? Consider basically any piece of open source networking software where we're accepting connections in on some thread that's like maybe an epoll loop, right? And then we have a set of worker threads that are running anywhere. And the memory from the connection is then, for the rest of the lifetime of the system, owned by one of these worker threads, right? All of these accesses are going to be remote accesses unless one of the worker threads is running on the same core as your event loop, in which case maybe you have other problems as well. So when we bring concurrency into the mix, we can understand that the additional latency can reduce performance. However, the performance degradation can actually be so bad that under high contention, atomic operations to remote memory can result in starvation, which means that threads that are trying to do some operation, some work, never actually get to run. It can also result in live locks, which means that threads on different processors are too busy trying to share memory with each other to actually get anything done because the processor is just jammed up queuing all of these memory operations. So there's some solutions to this. We can avoid the starvation problem by using something called fair locks, and these are locks that provide FIFO ordering. So if I request the lock with thread 0, and then I request the lock with thread 1, and then I request with thread 2, I'm guaranteed the ordering is going to be 0, 1, 2. However, these locks tend to have a higher fast path overhead, and they're also extremely sensitive to preemption and short scheduling times. As are basically all locks. However, there's been recent work around something called lock cohorting that's developed locks that are Numa friendly, also reader-writer locks that are Numa friendly. So you can look into that as well, and the paper again provides references to this topic. So that's about all for the environment. So let's get on to a better understanding of non-blocking algorithms, their guarantees, how they behave, how we can prove their correctness, maybe not formally, but at least how we can understand that they are correct, which is important. So let's start off by talking about the guarantees. So there's different classifications of non-blocking algorithms, I love the pig, that provide various guarantees on progress of operations. So wait freedom is the strongest of these guarantees, and it's also kind of the hardest to design for because it is such a strong guarantee. And what it says is that for any number of processes within a system, under contention, all of these processes will complete within a bounded period, within a bounded number of operations. So lock freedom is slightly weaker. It's still a system-wide guarantee, but what lock freedom says is that in a system with many processes, under contention, it is always true that at least one process will complete, will make progress through the system. Obstruction freedom is mentioned in the paper. It's weaker still. It only guarantees the completion of a single thread in the absence of contention or in the absence of preemption. However, most research into these algorithms and data structures tends to be for lock-free and wait-free algorithms. And the paper actually just kind of talks about this and skips over it as well, so that's what I'm going to do too. I would advise that you really don't have to worry about obstruction freedom. So good, let's see if we can visualize this a little bit. So let's consider a case, again, going back to the counter. So traditionally, we're going to write something where we've got some kind of lock, whether it's a spin lock, whether it's a sleeping lock, it doesn't matter. For something with this short of a critical section, with low contention, maybe a spin lock is fine. In our traditional blocking case, we're going to protect our critical region with a lock, and the region here is broken out into read, modify, and write distinct operations. I know I could have just written counter plus plus, but I'm really trying to sort of illustrate the fact that an increment involves a read, involves a modification, and involves a write, because again, we're talking about stuff in memory here, in shared memory. So what does this look like? So we have multiple threads attempting to access the lock. And in the contended case, where we're serializing threads on a lock, only one thread could make progress at a time. But this progress isn't guaranteed, because in your critical section, when you're preempted, potentially, even if you have preemption disabled, multiprocessing systems don't just run software infinitely, right? We have scheduling quanta, which is some period of time that we're allowed to run. Now, this may be, different schedulers work differently, but in general, you're not guaranteed that an operation is going to complete. And furthermore, if you run out of time, you might go to sleep. And during this time, no other threads can make progress. None, because you hold the lock Everybody else is waiting on you to release it. So there are no progress guarantees made by lock-based synchronization. Good. Let's talk a little bit about lock freedom and what would that look like. So again, we've got an interface to incrementer counter. This time I'm using CAS to do it. Whether that's implemented as an instruction or LLSC is really inconsequential. Doesn't matter. They both provide the same functionality. Again, we're reading, modifying, and writing a value. But this time, under contention, there's a system-wide guarantee that somebody's going to make progress. Somebody will complete the CAS operation no matter if there are threads that are stalled for any reason. So if we look at this visually, we can think of some number of threads where let's look at, say, the first thread where we have a much smaller critical section. And this, let's say, is time moving this way. And this is just our thread enumeration. So these are our critical sections, and we have contention because these are all happening at the same time. This guy wins. He completes. So these guys have to retry their operation because, remember, we've got some loop where we're trying to retry operations until they complete. So this time, this guy completes and goes. The ordering is sort of non-deterministic. You can't make a guarantee about who completes, but you can make a guarantee that somebody completes. And again, let's say there's only 3 threads in the system. This guy will retry, and in the absence of contention, because these other threads aren't contending, he will complete as well. Or she, if you have female threads. So finally, let's look at a wait-free version. What is wait freedom? Well, again, all threads are going to make progress, and this is an entirely simplistic form of wait freedom. There are wait-free versions of other algorithms and data structures, and sometimes those can be easy if you can constrain sort of the number of concurrent processes that you're working on, or that you have working at the same time. But because some processors do provide us with operations that perform read, modify, write, like an increment, even under contention, we're guaranteed to complete in bounded time. So what does this look like? So this atomic increment on our counter, no matter the contention, there's a bounded number of steps that this will take, at which point all of them will complete, and they will complete successfully. So I know I've been spending a lot of time talking about how things work in the face of contention, but what is contention really? So let's try to give it a more formal definition and sort of explore how it affects us. So contention is a product of the effective arrival rate of requests to a shared resource, which leads to a queuing effect that directly impacts the responsiveness of a system. What does this look like? So this isn't really right. This isn't pretty. It's pretty chaotic. So there's a ton of people. People are giving up and going away. People are cutting in line, like this person. By the way, this is apparently what you get to look forward to if you go to the Eiffel Tower. I haven't been, but maybe I won't. So one of the most awesome points in the paper, locks create queues. In the contended case, many threads contending on a lock, in effect, creates a queue of threads. Okay, so when I first read this in the paper, it completely changed the way that I thought about lock-based synchronization and concurrent programming. Even though I was already working with concurrent data structures and algorithms, this really inspired like a shift in my thinking. And I don't know if this idea is novel to the paper. I suspect it's probably not, because there's been a lot of research into concurrent systems for years and years and years. And it seems really obvious in hindsight once you hear it. But the paper, for me, really framed the idea particularly well. So the shift in thinking is this. If I'm implicitly making a queue in my system, why don't I just use a queue to represent the work that I'm doing? This point is so important that I will actually come back to it later when we go over our review, but in the interest of completion, let's just talk about other reasons that lock programming is perilous. We have lock order reversals, we have deadlocks, we have preemption sensitivity, scheduling sensitivity, we have problems with lock recursion. We're plagued by bugs resulting from the fact that writing lock-based software isn't really composable, or that lock-based software isn't really composable. It's hard to necessarily know whether a particular interface implies a lock is held, needs a lock to be held. We forget to lock. It's hard. Furthermore, although we've implicitly created a queue, it's not a FIFO, it's not a LIFO or FILO, or however you want to talk about a stack-based thing. Even with detailed knowledge of our scheduler, we can't make guarantees about order of execution of threads waiting for a lock unless we're using a fair lock. And I talked about some caveats of fair locks, but page 13 of the paper gets into that a little bit more as well. So to summarize, lock-based synchronization, no guarantees about completion, and the latency of the critical section directly impacts system throughput. So this seems logical, but can we prove it? Turns out we can. There's a direct relationship between latency and throughput, and it's defined by Little's law, which the paper points out is a result of queuing theory, which you might think is odd given that it's called a law. And it's a result because it was derived and it kept popping up in equations everywhere when Little was studying, I guess, information or queuing systems operation theory. So he found this out, and he published a paper about it, and it was initially thought to be true on common sense, but has since been proved multiple times in multiple ways. And what the law says is basically the number of waiters in a stable system, so the system's capacity, is equal to the completion time for servicing an item within that system, the latency of the system, times the arrival rate, throughput, L equals lambda W. So from our quote on the prior slide, contention is quite literally a mathematical product in which one of the terms is the arrival rate, which is defined, which is contention. It's defined by the number of waiters in the system. So this law gives us a number of other useful pieces for like modeling software and thinking about our software. If you know your request load and you know your latency for a particular operation, you can calculate your throughput. If you know your throughput and your latency, you can estimate your maximum request load. You can also use it to work backwards. I need to handle in requests over in threads. So you can use that to determine how much latency you actually have to work with within your critical region or within this section that you need to complete. So we can use this information to better understand our workload and define constraints on it. So on that note, let's talk a little bit about workloads without contention, just to think about things a little bit differently. Non-blocking algorithms aren't always appropriate. This really gets back to understanding both our execution environment, but also requires us to understand our workload, which I would also argue is part of our runtime environment, basically. So let's consider some example case where we've got some shared memory that's used for statistics or counters, which is super common. We're always like counting number of requests in a system, or pages served, or whatever it is. Imagine that we have a single thread that's responsible for writing this data. And let's imagine that we have a single thread that's responsible for reading this data. But that data is only ever read when you ask for it, right? You're never reading it unless you're like, hey, how many requests am I doing right now? And maybe that's part of your monitoring, so maybe you're getting that at a granularity of 1 second, but 1 request a second on a 2.9 gigahertz processor is no contention. That's not a contentious scenario. 10 times a second, 1 million times a second, maybe 1 million times a second, you could start thinking about it as being a little contentious. So the table presented here also comes from the paper, and it shows the latency to push and pop items from a stack on an Intel processor on this side and a power processor on this side without contention. This is the uncontended case. So what we see is interesting. It's actually more efficient to use the spin lock on the Intel processor than it is to use a lock-free stack on the Intel processor. We see, this is in cycles, by the way, so it took 17 processor cycles to obtain a lock, put the data in memory, and unlock. Whereas it took 25 to do the lock-free version. The opposite's true on power, right? So it took 29 cycles to acquire a lock and do the operation, whereas it took 12 cycles to just use the lock-free data structure. So why is this? So on the Intel architecture, the spin lock's cheaper because it can use a lighter weight atomic instruction. And the lock-free stack push and pop use a full CAS, which again implies also a heavy memory barrier. Though the lighter weight atomic instruction may not necessarily need to, or it may be implicit. Although I think, whatever. On power, it's the opposite. So remember I said on Intel we have the comp exchange instruction. On power we're using LLSC. On power we have to use LLSC for the spin lock and we have to use LLSC for the lock-free version. That's all we have to work with here. And so the spin lock in this implementation requires actually a full memory barrier, whereas the lock-free algorithm can use a partial load on the consume side and a partial store barrier on the produce side. So that really underscores why we spent so much time going over the memory model. So let's look at what happens when we actually bring contention into the mix, and this is pretty great. So what we're looking at here is a graph of a latency distribution of a push-only workload to the same stack data structure. Okay, the y-axis is latency measured in CPU cycles from 0 to 11,000 at the top. The x-axis is the quantile, so how many requests finish after 10% of our time, 90% of our time, 100% of our time. The red bars represent latency for waiting for a spin lock under contention. The green bars represent the lock-free stack push operation. Because non-blocking algorithms provide system-wide guarantees, this is the only reason that we observe lower latency distribution. Because as we saw in the previous slide, it could be the case that without contention that any individual access is actually really fast. So it doesn't actually matter here whether we're talking about this graph in terms of Intel or power. It would look the same. What matters is the system-wide progress guarantees that are made by non-blocking algorithms. So again, also remember that the throughput is directly tied to latency in a stable system. So as the latency increases, our ability to service new requests looks to degrade with some like either exponential or polynomial factor here. It looks pretty gross. So this is all great. How do we know that these algorithms actually work, right? We need to have something stronger than feeling of faith. Makes us feel warm and fuzzy to use them. They have to actually work, right? We can't use them in production otherwise. So in most cases, we consider these algorithms in terms of what are called linearization points. And these are places in the algorithm where some set of operations appears to complete atomically. Okay, so a non-blocking queue might allocate an object, or you might have an allocation and do some setup to an object, initialize some values, and insert it into this data structure head or tail, depending on what kind of queue you're using some atomic CAS variant. So the successful completion of the CAS is said to be the linearization point of the algorithm. Now, the more operations we require to initialize our data, the more complicated proving this stuff becomes, because either the initialization data needs to be completely inconsequential to concurrent operations, or we're introducing additional state. And due to the varying memory ordering semantics of processors, whether strong or weak, loads and stores, the ordering of them contributes heavily to the potential number of execution histories that a program can have. And because we have to know a total order of guaranteed state of memory at any point, the variability of ordering actually matters if we want to consider state space. So we get state space explosion, which is actually dominated by a factorial term. So this actually point about memory ordering brings me again to one of my favorite quotes of the paper, which is, what may seem like memory model minutiae may actually be a violation of correctness of your program. Okay, so last point on non-blocking algorithms, safe memory reclamation. If you're using a garbage collected language, C#, Java, Go, whatever, this section's probably not relevant to you, but just bear with me for a little bit longer. A popular mechanism for creating non-blocking algorithms is actually to decouple an object's liveness, which means the duration of time it actually has a valid backing in memory, with its visibility to the system, which means the duration of time that other processes could potentially find the data as active within the system. In unmanaged languages, so C, C++, this means that we now have to track an object's state, so when it's active, and also when it can be reclaimed. So the most familiar point, I think, for most of us is probably reference counting. It can perform poorly, especially when objects are frequently accessed and when they're long-lived. And we should know why now. There's going to be a ton of cache traffic because this is a case of constantly incrementing and decrementing a value. So ref counts are never cacheable. So some schemes try to ameliorate this a bit by moving away from the get a pointer, take a reference paradigm, by taking long-lived, infrequently updated references, but that can be confusing. It also weakens the guarantee of the ref count. And finally, it can be hard to do reference counting without locks. When a reference count is embedded into an object, without locked access to the reference count, the object actually has to retain its type after it's no longer visible to the system to guarantee safety. You may have to use something like deferred free, where you wait some period of time after which you say, I'm pretty sure that nothing's going to happen here. Actually, this morning, we had a case where a kernel stalled and a ton of threads got created. We had a ton of backlog. System went completely catatonic, and we do use deferred memory freeing, and we defer freed something that was still referenced. So the time matters. And this is like 2 minutes, right? It takes 2 minutes. So the system was like basically stuck for a long time. So even if you've got a time that's an eternity for a processor, that doesn't guarantee safety. So there are other mechanisms that exist that perform better and don't suffer from the complexity in terms of performance of reference counting. So Sami Albarra, who's again the author of this paper, is going to be presenting at PWL New York next Tuesday. From Thomas Hart's paper that's comparing epoch-based reclamation, hazard pointers, and quiescent state-based reclamation. And I really, if you found this interesting for some reason, I really highly recommend watching his talk to get a better idea of safe memory reclamation schemes and how they work and their performance implications in particular. Cool, so let's wrap up. We talked about our environment. We talked about how important it is to understand our execution context, the context in which our software is built, how we design our software, what our workload is. Without understanding processors, how they deal with caching memory, how they deal with memory ordering, and what atomic primitives we have to work with, we're doomed to write software that's inefficient, incorrect, or both. We also covered why it's important to understand the workload, because lock-free and wait-free algorithms aren't appropriate in all situations. And we discussed a particular use case, reading statistics, in which we may not want to work on this. Is anybody not working with Intel processors primarily? Yeah. So that's the use case. So we covered non-blocking algorithms, we covered their progress guarantees, we covered why lock-based algorithms are inefficient under contention. We talked about locks creating queues, and just to, again, get back to that point, many lock-free and wait-free algorithms are actually queuing data structures. So if you can reframe your problem in terms of work and requests, do you have ordering guarantees? Do you not have requirements? Do you not have ordering requirements? Do you have a fixed number of work items? Can you use a ring buffer? You can reframe your problem in terms of the work and the requests, and many of the issues that require lock-based synchronization for you right now don't. So a common case is logging. A lot of the time in our systems we're trying to log information, and if we're doing this in the fast path or in the path of our request, and this log is persisted to disk, or even if it's persisted to memory maybe, this can actually end up taking up a lot of the time that you're spending serving the requests. So we found this to be true in our software, and what I did was I used a lock-free stack because the ordering of these log items didn't actually matter, so they could be in reverse order. I have multiple producers pushing to the stack, and then I have a single consumer that just claims a reference to the entire stack and does an asynchronous process. We did some benchmarking for turning off these log algorithms, or I'm sorry, these log requests, operations, there's the word, and found that there was basically like no measurable difference in our ability to service requests with it on or off because all of our overhead was elsewhere now. So you can find implementations of a number of lock-free and wait-free algorithms in data structure form, safe memory reclamation, constructs, spin locks, plethora of algorithms and data structures, and also good documentation and readable code at concurrencykit.org, also a project that is maintained by Sammy. Also, while the paper has a number of really great references, I really highly recommend reading one of them, which is super long. It's basically a textbook, but it's Paul McKinney's book, Is Parallel Programming Hard? And if so, what can you do about it? It's also a living document. It's managed in Git. It's Creative Commons licensed. Really great. So finally, I want to give special thanks to Inez for her extremely generous help with the slide content, which, by the way, she actually did by prioritizing over studying for her naturalization test at one point at 9:30 p.m., which I gather she also passed, by the way. And also sitting through 2 dry runs of this. Also, major props to Sammy for writing the paper, providing concurrency kit, and also taking the time to look over my slides and make sure that they were at least marginally correct. Thanks to Tyler McMullen, Nathan Taylor, and Grant Zhang for looking at my slides and also making helpful suggestions. So that's all I've got for you today. So if you've got questions, I'd be happy to take them. And thank you.
All right, so we have 2 mics. Elaine is going to take, Elaine, do you want to take that section and I take this section? All right, who has questions here?
This is contention.
I didn't quite understand the spin lock versus atomic counter example. It seems like in both of those cases, for both of those data structures, only one thread could make progress at a time. So why does this result happen?
Yeah, so that was a thing that took me a while as well, and it's quite commonly sort of confusing because you notionally, right, one thread makes progress, but the point is that when you're in a critical section that's locked, if you go to sleep because you've done something like that you shouldn't do while holding a lock, like doing a syscall. But even if you have no syscalls, even if you have nothing that's going to put you into any sleeping state, the kernel scheduler, like I said, doesn't run your program forever. So your scheduling quantum can run out in the middle of your critical section, at which point you're interrupted and no other threads are making progress. So you have no system-wide guarantee. In the lock-based case, so we have these 3 waiters queuing behind a lock where only one completes, but it doesn't necessarily complete. I can stall on the read, I can stall on the modify, I can stall on the write due to scheduling or preemption, at which point nobody completes because everybody else is still queued behind the lock. So this gets back into the queuing. In this case, we don't really have a queuing. Okay. It's like you're queued at the Eiffel Tower, right? And the person letting you in falls asleep and nobody's getting through anymore, okay? Whereas here, you're guaranteed that at least once per time quantum, once per whatever, even if like 30 people are jamming to get through, only one person's going to get through at a time, but one person will get through, no matter if there's contention, no matter if the scheduling quantum runs out, no matter if they're preempted, no matter if somebody else who's trying to do the same read, modify, write set goes to sleep in the middle of doing the read, modify, write. So that's the fundamental difference here, is that although we do retry, somebody completes every time. Anytime there's contention or not, somebody completes.
Hey, Devon, would it be akin like whenever you have to feed your cat and you have to be there to feed it versus an automatic feeder? In that sense, at some point, somebody's going to get food, whether you're there or not. Would that make a better point?
I don't know how feeding works for your dog, but yeah. Yeah, there's any number of analogies that we could come up with. Does that help clear things up a little, or this one?
The graph.
Oh, okay. The graph. Okay.
Questions on this side? Yes.
Thanks.
Uh-oh. More contention.
Yeah. You go.
Here we have per thread resources, but I am a single consumer and I can't take both of them at the same time.
I was going to make an exponential back-off joke, but yours was better. So you mentioned...
Back off.
So you mentioned...
Back off, back off.
Oh.
Back off, back off, back off, back off. Go ahead.
Okay. So you mentioned in the LLSC case that you can get preempted in the middle of what you would nominally consider an atomic operation.
Yes.
Could you imagine either the hardware that favors that kind of atomic strategy or a lock implementation for LLC to just simply disable preemption?
It's not just preemption, right? Scheduling quantum's also involved, but even assuming no contention and even assuming no preemption, again, the processor has limited space to deal with the dependency chain for tracking the changes to the loaded variable and load linked. So if you have an explosion in number of things that you're linked loading, some of them will fall off, and if those are the ones that call store conditional first, those are going to fail. And if you're continuing to queue these items, right, it can any jitter in the system can sort of exacerbate this case.
Okay, cool. All right, thanks.
So for a complete noob on this, how paranoid should I be about all the optimizations that can happen on any level of this? Or how much can I assume that the compiler takes care of me? How much can I assume the OS takes care of me? And what, I guess, signals should I be looking for to investigate more and actually try to get to the bottom of stuff?
You should be very paranoid. So a year or two ago, I was visiting Sammy, and he and a colleague of his were investigating some bug with, I think it was the concurrent ring buffer. And everything looked great. The code was great, linearized properly. Everything was wonderful. We looked at the disassembly, and I found that the compiler had reordered an instruction that it was told not to reorder. Okay, so there's a compiler bug right there. The best that you can do is test under contention, test under high contention, get systems with lots of processors and test more on those, and then observe whether it fails. Compilers are usually pretty good. That was, I don't remember if that was GCC or CLang. I think it was GCC 4.8 or something like that. As far as the operating system goes, scheduler is something to keep in mind when you're thinking about using blocking synchronization. Numa is something to keep in mind, so that you have good throughput, low latency when you do have to access memory. But yeah, paranoid.
I'm curious, is there some good usage of lock-free algorithm in distributed system?
Sure. We have a distributed system for our purging infrastructure at Fastly that uses a concurrent hash table to store messages that are outstanding within the distributed protocol, so that it can know whether it needs to resend them or broadcast them. Yes, it's useful. I don't think just for distributed systems or just for systems programming. It's useful in any system where you're talking about scalability and you're talking about high performance, low latency workloads, where you need to potentially make guarantees on system progress, where you may have latency guarantees that you may need to provide for a customer. So say you're an ad bidding network and you need to make sure that all of your bids are, executing within some millisecond bounded amount of time. You don't get those guarantees with lock-based algorithms, with lock-based synchronization. I can't think of any particular case that they would be particularly better for distributed systems, other than distributed systems tend to also be implemented as, or try to be implemented as scalable systems. So if you can scale up on your hardware, it also reduces the need for you to scale out to distribute your workload.
Also, sorry, another question is about the latency. You mentioned the lock-based algorithm maybe have unlimited latency, but how lock-free algorithm can avoid that? I think probably some thread can also forever retry and can never get the chance to. It's
theoretically possible. I don't know what kind of workload that would be. I haven't seen it, but I would actually point you to a paper from 2013 called "Are Lock-Free Algorithms Practically Wait-Free?" And this is a paper in which they implemented a stochastic scheduler, so it randomized ordering of execution of threads, and found that there was basically an upper bound to the amount of time that any particular thread took to complete. So from that perspective, you might even be able to extrapolate that in practice, lock-free algorithms are wait-free, and that answers your question. It's a little bit of a hand-wavy answer, but that's what I've got for you.
So assume I am extra paranoid and I want to look into these things or try some of this out myself. Like, what sort of tools would you use or could I use to, say, recreate this? Like, are you just literally taking like the DTSC?
Concurrency kit.
Okay.
Okay, so concurrency kit is ground up. Okay, so what it does is it provides a portable interface for access to processor provided atomics, whether those are increments, any set of read, modify, write, provides portable access to memory barriers and all of these under this CKPR interface. On top of that, it builds a number of data structures and spin locks and safe memory reclamation mechanisms, such as proxy collection, which is one I didn't talk about. Proxy collection is where you have ref count still, but you attach multiple object references to one ref count. So if you've got 5 references to this guy and 5 references to this guy, the proxy collector has 10 references. And both of the objects will go away when the proxy goes down to 0. Has implementations of that, hazard pointers, and epoch-based reclamation. The source code is extremely readable if you're familiar with C. The style is quite nice. It's based on BSD Style 9 guidelines. And so I think that that's, if you're trying to figure out how to piece together the pieces to actually create these data structures, that's where to go. I recently, and this is also a really important question, actually. I'm glad you brought it up, because it's not necessarily true that the lock-based stacks, queues, whatever, are always going to be correct for your workload. You may have some initialization, for instance, that needs to happen on your items before the linearization point that doesn't actually just really, it gets really close, but it doesn't fit into the interface that you're provided by CK. And so understanding how to put these primitives together can allow you to create specialized workloads, which I did for durable memory allocator recently, which is pretty cool. So, and it's based on the stack mechanism. So, yeah.
Following up on that, so I use some of these primitives I want to measure against my application that use locks. How can I build this graph, let's say, or what are you using the timestamp counter and just counting cycles outside of?
This graph was, yeah, it's RDTSCP.
Okay.
Yeah.
Do you use in your day job any other tools you find?
Perf.
Perf. Okay. Cool. Thanks.
Perf's really great, right? Because it also lets you get cache misses, branch miss predictions, and all sorts of other things that the processor can and does track for you. Also, there's software events that can be useful. You can see context switch time. I also recommend Brendan Gregg's flame graph suite, which can take perf output as well as dtrace output and output of other profiling applications and create really awesome flame graphs so that you can see where your latency actually is.
So my question is way more general, and that's, how would you use, or how would the knowledge that's in this paper affect how you would write code in a high-level language such as, say, Python or PHP?
That's a hard question. So I think my useful suggestion to you was in the first 3 slides, or to that person, which is the information in this paper really tells you a lot about the environment, the runtime environment that you're executing in. So you are in Python or PHP or whatever, very, very far away from memory. You may even be executing in the context of a web server or some, fast CGI or server module or whatever, right? You've got a lot under you. And so understanding how processors work can sort of bubble up some information, like maybe I shouldn't create a lot of garbage. Maybe I should reduce the number of variables that I'm using, because the more variables I have, the more memory I'm using. If I'm using memory, can I group things together in something that maybe the language's runtime provides me some kind of contiguous array, so I can, so if you've got an array of counters that are accessed by one thread, say, or concurrently, maybe you're using stackless Python, I don't know. Is that still a thing, by the way? I don't know. If that's provided to you, then you can use that to your benefit, because you know, okay, well, this is contiguous memory. If I read 8 bytes at the beginning, I get 64 bytes. So that means that the rest of if you're doing this in a tight loop, right? Your tight loop will be in cache, basically, and you can use that for things like loop unrolling. That's maybe a little bit better if you've got maybe you're in Lua and you're using LuaJIT, so you've got a jitter. Maybe you can use that to your advantage. Finally, I think that in more general terms, you need to understand your runtime environment as well. So if you're running in PHP or in an interpreted context, take the time to understand what happens. I mean, a lot of the reason that people rag on PHP is because the scripts are parsed every time, right? In web server context, unless you use one of these PHP caches like APC or whatever. That adds to overhead, and so Python caches bytecode in its, as far as I understand, in its integrations with Apache by default. So, and it also pre-compiles and does all, whatever, I don't know. I'm not a Pythonista, but understanding all of your environment, I think, is the best way. Getting a little bit back to your question about distributed systems as well. Distributed systems can also be concurrent systems, and when you're dealing with web systems, you may not have shared memory per se, but you may be accessing databases, so now you need to understand transactional access to database. That's effectively a mutex, right? You've created a critical region around your thing, and it actually probably is implemented with some kind of lock-based synchronization at the level of the database itself. So there's a lot of ways that you can kind of take these things and translate them up the stack as well.
Yeah, I just had a quick question. Earlier, about 5 minutes ago, you were mentioning that you found a bug in GCC, like there's some missing fence instruction. How are you able to determine that it was a GCC a compiler problem versus something in like the CPU instruction reordering?
Yeah, so maybe I explained that poorly. So what it was is that there was compilers can reorder instructions or reorder operations in your program so that to optimize for the processor. And so they'll do this because your processor has a pipeline, and this allows it to load multiple instructions from memory into the pipeline and execute them in an out-of-order execution engine, and then wait for the results to come back. So if you pipeline instructions in a certain order, then what you end up with is some of the operations finishing before others. And if you do things right, ideally all of the operations appear to complete at the same time, and you've waited the lowest number of cycles you possibly could because you pipelined your longest latency instruction, maybe a division, which might take, I think, 5 cycles, with maybe a couple of additions or something that are a half cycle or a cycle each. So maybe you've done all that, or the compiler's done all that for you. So what happened here was that we had put a compiler barrier. So you can do this in C with the volatile keyword, which keeps variable access from being reordered only in terms of other volatile targeted things, by the way. Or you can use an inline assembler, empty inline assembler construct that says that it clobbers memory. So it lists memory in the list of clobbers. And that tells GCC not to reorder anything that happened before it. What had happened was that was that clobbers memory was part of this atomic operation for the wait-free actually in queue to the ring buffer. However, what had happened was that GCC had determined the thing that was being operated on was a loop invariant, and taken the assignment out of the loop. And so that was the reordering that happened.
Damn, that's some debugging.
And I just used optjump for that, optjump-d, and that'll disassemble any binary executable format on Linux. OTool for Mac, I think there might be others.
Okay, so that wraps up the Q&A. The generous and lovely folks at GitHub have let us stay here for a little bit longer, so you can grab a drink, chat more, let us know if you have any questions, and we'll see you next month. Any other last-minute announcements?
Now that said, the date for next month may change. Sorry, Sargon, we're gonna have, we have some conflict, so.
Surprise!
Surprise! So we're gonna have to check with you, and if you're a mini speaker for next month, you'll be hearing from me soon. So thank you everybody for coming.
Thank you, and another, yep. Yay!